Hello, my dear students. Welcome to IKSR chemistry classes. Here we are in lecture number 7 on ESR spectroscopy applied to inorganic chemistry. Let us start our discussion with origin of hyperfine splitting. In the previous video, we have already discussed hyperfine splitting, which is nothing but the splitting up of ESR signal into various components, into various hyperfine lines. And now we will discuss the origin of hyperfine splitting. The origin of hyperfine splitting can be explained by considering the following fragment of an aromatic system. This is a fragment of aromatic system in which carbon atom is sp2 hybridized, forming 1, 2, 3 sigma bonds and 1 pi bond. It contains one unpaired electron. This unpaired electron spends time mainly around carbon atom, but it also spends some time around the nucleus of hydrogen atom. The CH bonding orbital, the CH bonding orbital is formed by the overlapping of singly occupied sp2 hybrid orbital of carbon atom and singly occupied 1s atomic orbital of hydrogen atom. This CH sigma bonding orbital is formed by the overlapping of singly occupied sp2 hybrid orbital of carbon atom and 1s atomic orbital, which is also singly occupied, of hydrogen atom. Thus, this bonding orbital is occupied by 2 electrons. The CH bonding orbital is occupied by 2 electrons and carbon atom contributes 1 electron while hydrogen atom also contributes 1 electron to this CH bonding orbital. This CH bonding orbital is produced by the overlapping of singly occupied sp2 hybrid orbital of carbon atom and singly occupied 1s atomic orbital of hydrogen atom. The unpaired electron of benzene radical anion is present in 2p atomic orbital of carbon atom. In the case of benzene radical anion, the unpaired electron is present in 2p atomic orbital of carbon atom. The following two structures are possible for these electrons. There are 3 electrons. 2 electrons are present in CH bonding orbital and 1 electron is present in 2p atomic orbital of carbon atom, and 2 structures are possible for these 3 electrons. This is possible structure number A and this is possible structure number B. The configuration A, this one, is more favorable than configuration B because the carbon spins are parallel to each other. This configuration A is more favored than configuration B because in configuration A, 2 electrons of carbon have parallel spin, there will be exchange interaction between them which stabilizes the system. This electronic structure is more stable, is more favorable than electronic structure B, because in electronic structure A, two electrons of carbon atom have parallel spins, while in electronic structure B, two electrons of carbon atom have anti-parallel spin. Please note that in CH bonding orbital, two electrons have opposite spins. It is clockwise, it is anti-clockwise. In this case also, it is anti-clockwise and it is clockwise. In CH bonding MO, two electrons must have anti-parallel spins. But in electronic structure A, two electrons of carbon atom have parallel spin, while in electronic structure B, two electrons of carbon have anti-parallel spins. We should know a term exchange energy and exchange interaction. If the exchange of positions of two electrons in the space does not lead to change in any electronic arrangement, it leads to decrease in energy of the system, which is called exchange energy, and this phenomenon is called exchange interaction, and it can take place only when the spins of two electrons are parallel. In electronic arrangement A, two electrons of carbon atom have parallel spins and there is exchange interaction between them which stabilizes the system, and therefore electronic structure A for the given aromatic fragment is more stable, more favorable than electronic arrangement, electronic structure B. The result is that there will be a small amount of unpairing of electrons in the CH sigma bonding orbital. As a result of this exchange interaction in electronic structure A, there will be some unpairing of electrons in CH bonding orbital. It means this polarization of electron will produce some unpaired spin density on hydrogen atom as illustrated in the following figure. As a result of this polarization, as a result of this exchange interaction, there will be some unpaired spin density on hydrogen atom. There is exchange interaction between these two electrons of carbon atom. There is exchange interaction between these two electrons of carbon atom having parallel spins. And due to this exchange, this electron will behave like an unpaired electron. Due to this exchange interaction, this unpaired electron will behave like unpaired electron. It means the unpaired electron of carbon atom spends some time near hydrogen atom. The hydrogen atom nucleus has some unpaired electron density around it, and there will be coupling between the nucleus of hydrogen atom and this unpaired electron. There will be no coupling between this electron and nucleus of carbon, because the nucleus of carbon has I equals to 0. Nucleus electron coupling will take place only when the nuclear spin is non-zero. The spin of carbon C12 I equals to 0, and there will be no nucleus spin interaction. But in the case of hydrogen atom, I equals to half, and there will be nucleus spin interaction, because this electron behaves like unpaired electron around the nucleus of hydrogen atom. However, this effect is small, and separation between consecutive lines in the ESR spectrum of benzene radical anion is only 0.38 millitesla. The spin nucleus coupling in benzene radical anion is weak, is small, and this is why the spin nucleus coupling constant is only 0.38 millitesla. It means there is only a small unpaired electron density around the nucleus of hydrogen atom in this fragment. Hyperfine coupling constant. It is also known as electron-nucleus coupling constant. The separation between two consecutive hyperfine lines, the separation between two consecutive hyperfine lines in an ESR signal is called hyperfine coupling constant or electron-nucleus coupling constant. Please see it again. The separation between two consecutive hyperfine lines in an ESR signal is called hyperfine coupling constant or electron-nucleus coupling constant. It is denoted by a small a or capital A. It is generally expressed in Tesla or millitesla. Please note that 1 millitesla is equal to 10 to the power minus 3 Tesla. The greater the value of A, the greater the value of hyperfine coupling constant or electron-nucleus coupling constant, a stronger will be the electron-nucleus coupling. A stronger the electron-nucleus coupling, greater will be the value of A. Let us see an illustrative example. It is the ESR spectrum of electron in hydrogen atom in the presence of magnetic field of strength B. It is clear that the ESR spectrum of hydrogen atom consists of two hyperfine lines with intensities in the ratio 1:1. The separation between these two hyperfine lines in the ESR signal of hydrogen atom is called hyperfine coupling constant or electron-nucleus coupling constant. It is denoted by E. And in the case of hydrogen atom, the separation between these two hyperfine lines is equal to 0.05 Tesla. It means here the hyperfine coupling constant or electron-nucleus coupling constant for hydrogen atom is 0.05 Tesla. Coupling constant and electron density. Here we have two nuclei, the electron density around this nucleus is lower, while the electron density around this nucleus is higher. The coupling constant A is directly proportional to the electron density around the nucleus. Greater the electron density around the nucleus, a stronger will be the electron nucleus coupling, and consequently higher will be the value of coupling constant A. A is directly proportional to electron density, that is rho, and it can be written as A is equal to R into rho. Here R is proportionality constant. Here rho is electron density around the nucleus. It is electron density around the nucleus. R is intrinsic coupling constant. It is proportionality constant. It is known as intrinsic coupling for unit electron density. If the electron density is unit, then A is equal to R, and therefore R is called intrinsic coupling for unit electron density. R is proportionality constant. And if the electron density around the nucleus is unit, A is equal to R, and this is why R is also known as intrinsic coupling for unit electron density. Intrinsic coupling R. This is hydrogen atom, and it's a ESR spectrum. In the case of hydrogen atom, the electron is localized around only one nucleus. In the case of hydrogen atom, this electron is localized around only this nucleus. This electron is localized only around this nucleus, and therefore the electron density rho around the nucleus, that is around the proton, is unity. This electron is localized around only one nucleus, and therefore the electron density around this nucleus, that is proton, will be equal to 1. Therefore, from the equation A is equal to R into rho, we have A is equal to R into 1. Since the electron density around this nucleus is 1, this electron is localized only around this nucleus. It means A is equal to R. But in the case of ESR spectrum of hydrogen atom, the value of A is 0.05 Tesla. It means R is equal to 0.05 Tesla. The intrinsic coupling for unit electron density, that is R, is equal to 0.05 Tesla. This value will be put for R in further discussions. There is a problem assignment for judging yourself that how far you have learned the previous discussions. The separation between two consecutive lines in the ESR spectrum of methyl free radical is 2.3 millitesla. Calculate the unpaired electron density on each hydrogen atom and on carbon atom. In the ESR spectrum of methyl free radical, the separation between two consecutive hyperfine lines is 2.3 millitesla. Then we have to calculate the unpaired electron density on each hydrogen atom and on carbon atom also. It is methyl free radical. It contains one unpaired electron which can be delocalized around the nucleus of three hydrogen atoms. It is the ESR spectrum of methyl free radical in which the separation between two consecutive hyperfine lines is 2.3 millitesla, and thus it is the value of hyperfine coupling constant A. We know that A is equal to R into rho. The value of A is given 2.3 millitesla, which is equal to 0.0023 Tesla. The value of R is 0.05 Tesla as we have discussed earlier, and into rho. On this basis, the value of rho is equal to 0.0023 Tesla divided by 0.05 Tesla, and it is equal to 0.046. Thus, the electron density around one proton is equal to 0.046 or 4.6%. The electron density around all these three protons will be equal to 0 into 0.46 into 3 is equal to 0.14, that is 14%. 14% electron density is around 3 protons, and therefore the electron density around carbon nucleus will be 100 minus 14, that is 86%. The unpaired electron of methyl free radical spends 4.6% time around each proton of the hydrogen nucleus and 86% time around the nucleus of carbon atom. There is another problem for self-assessment. The separation between two consecutive lines in the ESR spectrum of benzene radical anion is 0.38 millitesla. Then calculate the unpaired electron density on each hydrogen atom and on carbon atom. It is benzene radical anion. It has one unpaired electron which spends time around all the 6 carbon atoms and 6 hydrogen atoms. It is its ESR spectrum in which the separation between two consecutive hyperfine lines is 0.38 millitesla. We know that A is equal to R into rho. Here A is 0.38 millitesla, that is 0.0038 Tesla. There should be one zero more. It is 0.00038 Tesla divided by 0.05 Tesla into rho. On solving it, rho is equal to 0.00038 Tesla divided by 0.05 Tesla, and it comes to be 0.0076. The electron density around each hydrogen atom, the unpaired electron density around each hydrogen atom is 0.0076 or 0.76%. Electron density around 6 protons, there are 6 protons, it will be equal to 0.0076 into 6, that is 0.05. This is the approximate value. or 5%. The electron density around 6 carbon nuclei will be 100 minus 5, that is 95%. It means the electron density around 1 carbon nucleus will be 95 by 6, that is about 16%. Let us see it again. The unpaired electron of benzene radical anion spends 0.76% time around the nucleus of each hydrogen atom and 16% time around the nucleus of each carbon atom. Thank you for watching the video with concentration. Please like and share it. And if you have not subscribed my channel yet, please subscribe it so that you get information regarding my new videos in time. Thank you.